Let's answer another stoichiometry question from an old grade 12 examination. Here's a question involving equilibrium. We start off with some hydrogen and some iodine that are sealed inside a container. So at the start, all that is inside this container is some hydrogen and some iodine, nothing else. There's not yet any hydrogen iodide. But we leave the reaction, and in time it reaches equilibrium. And at equilibrium, we have all three of these chemicals. Why? Because some of this hydrogen has reacted with some of this iodine to produce hydrogen iodide. So now here we have this 2 decimeter cubed, which is the same thing as 2 liter container. And at equilibrium, inside this container, we have so much hydrogen, so much iodine, and also some hydrogen iodide. Doesn't tell us how much. And we're asked to calculate the initial mass of iodine in grams that was inside the container at the beginning. Remember, initially, this container only had hydrogen and iodine. And we are asked, how much iodine was that in grams? And we're also told that Kc for this reaction is 55,3. Obviously, temperature is important, so that's why it gives us the temperature. So what is this question actually asking us? Let's first understand the equilibrium situation before we get to the real question. So we're told at equilibrium, we have so much hydrogen, so much iodine. We know that there must be some hydrogen iodide as well. Otherwise, it wouldn't be at equilibrium. We're given Kc for the reaction. It's 55,3. Now, we know that Kc has to do with concentrations, whereas at the moment, the information we're given is numbers of moles, not concentration. So the first thing we need to realize is that we need to convert these values into concentrations. And we know that concentration is equal to number of moles divided by volume. So let's quickly calculate the concentration of hydrogen and of iodine at equilibrium. We are told that we have 0,028 moles of hydrogen at equilibrium, and the volume of the container is 2 decimeter cubed. So at equilibrium, the concentration of hydrogen that we have is 0,014 mole per decimeter cubed, which is the same as molar. And the concentration of iodine that we have at equilibrium is the number of moles that we have, 0,017 moles, divided by the volume of the container, 2 decimeter cubed, 0,0085 molar. But how does that help us? Remember that Kc for this particular reaction is equal to the concentration of hydrogen iodide raised to the power 2 divided by the product of the concentration of hydrogen and iodine. The product of, in this case, means multiply. So we have the concentration of the product, Hi, raised to the power of its coefficient, 2, divided by the concentrations of the reactants, each raised to the power of their coefficients, which are, in both cases, 1 multiplied by one another. And we're told that the answer of that is 55,3 at this particular temperature. So how's that going to help us? Just remember, we've already just calculated that the concentration of hydrogen that we have is 0,014 molar, and the concentration of iodine that we have is 0,0085 molar. It's easy to see because it's simply half the number of moles, since the volume is 2. So to get the concentration, we have to take the number of moles, in this particular case, divided by 2, because of the volume being 2 decimeters cubed. So to make some progress, we need to find out what the concentration of hydrogen iodide is at equilibrium. And this fact here will help us, because we know this, well, obviously we know this. The only unknown is the concentration of hydrogen iodide, so we can find that out. So we make ourselves a sub-question for this main question we're asking, and that is, how many moles of hydrogen iodide are present in the container at equilibrium. So we need to find out the concentration of hydrogen iodide. It must be raised to the power 2. We know the concentrations of hydrogen and iodine. Look back if you've forgotten, but they are 0,014 molar, and we must multiply that by the concentration of iodine at equilibrium, 0,0085 molar. And that equals 55,3. So we multiply both sides by this number. To clear the fraction here, we have HI concentration squared is equal to 55,3 multiplied by 0,014 multiplied by 0,0085. We square root both sides. The concentration of HI is equal to the square root of all of this. Well, let's just quickly find out what is the product of all that, and then we put it under the square root sign. So we do that on our calculator, and we find the answer is 0,00658. Don't clear your calculator. We square root that, 0,08. And again, don't clear your calculator. 112 you can add if you like. What is this? We were calculating the concentration of hydrogen iodide at equilibrium. Now we look back at our question. What was the question? How many moles of hydrogen iodide are present at equilibrium? That's not the same thing. We've calculated the concentration. Now we need the number of moles. But we know that the number of moles is the concentration multiplied by the volume. We have the concentration, 0,08112 molar. We have the volume, 2 decimeters cubed. We still have the concentration on our calculator. We simply multiply it by 2 and we get the answer 0,1622 and so on. Again, don't clear your calculator, and that is moles. So we've now answered the question, how many moles of HI are present at equilibrium? And that was 0,162. So what is happening here? We had a sealed container, 2 liters, and at the start we had a certain amount, we don't know how much, of hydrogen and a certain amount of iodine and no hydrogen iodide. Only those two. Then they reacted together, and over time, now this is not a new container, it's the same container just a little later, it reached equilibrium. At equilibrium, it now has 0,028 moles of hydrogen, 0,017 moles of iodine, and it also has 0,162 moles of hydrogen iodide. Where did they come from? They were not there at the start. At the start, there was no hydrogen iodide. So where did that hydrogen iodide come from? It came when some of the hydrogen and some of the iodine reacted with one another to make this hydrogen iodide. And when they reacted, that's how much hydrogen iodide they made, 0,162 moles of hydrogen iodide. So let's summarize what's happening here. This is at equilibrium. So at the start, we had no hydrogen iodide. We don't know how much hydrogen we had. We were not told that. Nor do we know how much iodine. But we're very interested in that because that's actually what we're being asked. So that is really what we're interested in. And then we're told that at equilibrium, we have 0,028 moles of hydrogen, we have 0,017 moles of iodine, and we've just calculated 0,162 moles of hydrogen iodide. So what we've been doing so far is just trying to make sense of the situation. Now we need to try and think, how can we use that understanding of the situation to actually answer the question? In other words, to get this initial mass of iodine. So let's think about just that initial mass of iodine and what has happened to it. So let me represent the initial mass of iodine as a block here. There was a certain amount of iodine at the start. We have to find out how much that was. And then something happened during the process of getting from the start to the equilibrium situation. What is it that happened? Some of this initial iodine reacted. We don't know how much. So I'm not doing this to scale, but let's say this amount reacted. When it reacted, it became part of the hydrogen iodide. It's there now. Or to put another way, it's inside there. It's not all of that 0,162 moles, it's just some of that 0,162 moles, because some of its mass comes from the hydrogen. But the point is, it's not present anymore at the end, at the equilibrium situation, in the form of I2, because it has become part of the HI molecule. So at the end, we only have this 0,017 moles, the part of the initial that did not react. So what that tells us is that the whole of the initial is 0,017 plus whatever this was, let's call it X, that reacted. So if we could know how much iodine reacted and ended up inside the HI, we simply add that to how much is still there, 0,017, then we know how much there was at the beginning. Because the amount at the beginning is the amount that's still there, plus the amount that's changed in the process. So how are we going to find out how much changed? The first thing to realize is a very simple thing to see, and that is that 0,16224 moles of hydrogen iodide was produced during the change, during the reaction. And that's our key, because from that we can calculate how much iodine must have reacted in order to produce that amount of hydrogen iodide. So we write ourselves another sub-question. How many moles of iodine were needed so that we could produce so much hydrogen iodide? How many moles of iodine are needed to produce 0,16224 moles of hydrogen iodide? We know we must multiply this by a reaction ratio, a conversion factor, which comes from what we know about the mole reacting ratio. We know that 1 mole of hydrogen reacts with 1 mole of iodine to produce 2 moles of hydrogen iodide. That's the reacting ratio, the general reacting ratio that always applies. It's not the specific case now, not the actual amounts now. And that's what we need for a conversion factor. We must make sure that moles of iodine are at the top and moles of hydrogen iodide at the bottom. And we know that we need 1 mole of iodine to produce 2 moles of hydrogen iodide. So we get the answer, 0,08112 moles of iodine. So now we know X, we know how much iodine had to react in order to produce this much hydrogen iodide. But remember, that's not what the question is saying. That's just our sub-step question that we made for ourselves to help us. Remember, the actual question was about the initial mass of iodine. 0,08112 mole is first of all not mass, it's number of moles, but it's also not the initial amount. It's the amount that was changed. So we still need to substitute it into this equation up at the top to find out, well, how much was that whole amount? 0,08112 plus 0.017. So we find that this is the initial number of moles of iodine, 0,09812. But again, that is not the question. The question said calculate the initial mass in grams. So we make ourselves yet another sub-question. What is the mass of so many moles of iodine? What is the mass can also be written as how many grams is the mass of 0,09812 moles of iodine. We multiply it by a conversion factor where both top and bottom must refer to the same thing. And in this case, it must both refer to 1 mole of iodine, I2. And at the bottom, we actually have a mole of iodine. And at the top, we need the mass of that. 1 mole of iodine is, of course, 1 mole of iodine. But what is the mass of that? Multiplied by 2 because it's I2. We do that on our calculator and we round off to 2 decimal places. And we find the answer is 24,92 grams of iodine. Let's just summarize what did we do to solve this problem, because it consists of many steps, so you can get confused. We used the Kc value to calculate the number of moles of hydrogen iodide that were present once equilibrium had been reached. We were already told the numbers of moles of hydrogen and iodine that were present at equilibrium. So then we knew everything about the equilibrium state. We knew that at the start, there wasn't any hydrogen iodide. All the hydrogen iodide came from hydrogen and iodine reacting together inside the container. So all of this hydrogen iodide was produced by the process. And from that, we could deduce how much iodine had to react in order to produce that much hydrogen iodide, because chemicals always react in predictable ratios. So if you know how much hydrogen iodide there was produced, then you just calculate how much iodine must have reacted to produce that. And that's what we did. So then we knew how much iodine reacted. And we know that all of that, plus everything that was still there at the end, was present initially. So if we add the two together, that tells us how much iodine there was at the start. But we remembered that that gives us the number of moles of iodine, but we were actually asked the mass of iodine. So we simply had to convert that number of moles into grams, which is what we did now in this last step.